Okay, welcome back. We just got done with our 20-minute break and we kind of swapped out the equipment. And so this is, again, day 13, second lecture. And so we just finished our chapter 15 on waves in general. Let's get started with 16 now. 16 is specifically on sound waves. And I thought during the break to myself, I said, you know what, I've got a good animation for standing waves. And I was trying to draw it on the board and I realized, man, I wish I would have set up that animation. So during the break, I set up the animation and I go, even though we should really move into chapter 16, I thought, let me just show you that animation real quick. And so come over here. Let's look at the computer screen here. The computer screen, I've got some animations that I want to use for this particular chapter, but also here's the standing wave. And you can kind of see what I was getting at here in the animation is that if you look at the blue wave is traveling to the right. And if you look at the green wave is traveling to the left. And if you can add those together, you would get the red one. And so the red one is the superpositioning. That is, you combined the blue one and the green one together, this is what you would get. In fact, if I just kind of stop it in its motion right here, you'll see that right here, this is the antinode. This is the red one, is the combination of this height of the green one and the height of the blue one. This node right here is a combination of the height of the green one and the height of the blue one. If I move the waves one step there, maybe a second step, maybe a third, maybe a fourth, you kind of see that same thing. What you're beginning to see is you're beginning to see the blue and the green one come together where the crests line up, and then the red one's going to be way up here. But you will always see these magical points called the nodes that will always have the green up and blue down, or blue up and green down, so that they always add up to zeros. And so it doesn't look like it's moving anywhere. And if I just kind of step, 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 you can see that you always get the superpositioning of them. And this is isolation, but it's only for that one moment in time. And so not only are the nodes zero, because they're always zero, but every place else. And so the red line is flat. So I thought I would go ahead and let you kind of look at that animation here, because I think that does a much better job than my picture was, because it can show time and I don't have to draw pictures on top of themselves. So with that in mind, I'll kind of shut that off here and say, all right, let's go ahead now and get started with chapter 16. And so what is in chapter 16? And as I've alluded to quite a few times, 16 is sound waves. And I'll say it again, one thing nice about this chapter is that a lot of the properties of waves, even though we haven't explicitly said sound waves, we've already covered. That's why chapter 15 was such a powerful chapter. We talked about all these wonderful properties that waves have, and they have them for sound waves, and for light waves, and for radio waves, and for gamma rays, and the list goes on and on. All those waves have those same properties. And so you'll see that we'll just reach back to the last chapter as we do a lot of them. But I think the first place to begin is, what is a sound wave? And maybe I'll begin by just coming over here and grabbing one of these tuning forks that I've got hiding over here. This looks like a good one. Oh, here's another good one. Maybe I'll just work with these two. Maybe something I can strike it on that won't damage it here. But if I hit this, and usually I'd hold it out to the room, but maybe for you guys I should hold it close to my lapel mic. And so, okay, you know, hopefully you hear something. But I want to convince you that what you're hearing comes from this piece of metal going back and forth. And so I hit it, and I stop it. Okay. And so that gives us kind of an insight really to what sound waves are. Sound waves are this. If I can kind of draw a picture here. Here's the tuning fork, so here'll be the handle of it. And the metal piece kind of arcs up and looks kind of like a U shape. And I hit it. And what is happening on a microscopic level is the U is vibrating. It's going back and forth. I'll only draw one side. Well, I'll put the other side there. But I'll focus my attention only here on the right side of this U going back and forth. Because we'll see, here's what's going to happen is this U piece is going to come back, and then as it goes forward, it hits the air molecules that are in front of it. Then those hit the next ones, and then hits the next ones, and then hits the next ones, and hits the next ones, and hits the next ones, and then eventually it comes over here to something that records the hitting. That is, it could be an ear or it could be a microphone. It looks a little bit like this. This is what we called in the last chapter a longitudinal wave. Because when you bump the first one, then it bumps the second, which bumps the third, which you go all the way down, and eventually this last one gets moving. And so if the original bumping happens here, but the recording device, and so let's say right here is the ear, if I were to put my marker here, you would say push. Yep, pushed it. And if I would give it a pattern, push, push, pause, push, 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 pause, push, 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 pause, it would be hitting this instrument, which in this case my eardrum, at the same rate that we had initiated. And so this is our sound waves. This is a long way of saying what I mentioned in the last chapter, that sound waves are a type of longitudinal wave. I don't think I went as far in the last chapter to point out the microscopic picture of what's going on, but that's what I'm trying to do now. And so it would look something like this. This would come back and it would then, what you might say, compress a bunch of molecules right there and kind of slams them together. Which, as I said, those slam the next and slam the next and slam the next. And so after a little bit of time, that little compressional area has now moved away from the tuning fork. And if at the same time Ron, did we check the microphone? Oh, good, okay. So if we come back and slam it a second time, then we would get another group. So I'll leave this picture here to indicate this is the second time this piece of metal has hit. So the first time they've already moved away, and now we have a second one. And then, of course, this process would repeat a third time. As this is coming back and slamming it a third time, the original one would have keep hitting more molecules, and so that original little space of compression is now here. And the second one has now moved here. And now this is the formation of the third one. And I'll stop with my drawing there because I think that hopefully indicates that this is just going to keep repeating. And so what we have then is a wave. That is, over here, if there is some kind of detector here, picking it up, this detector would then physically move back and forth, mechanically move back and forth. These molecules here would actually then come in and be hitting it at the same rate that this metal piece is going back and forth. So I would say that from here over to here, we have a wave, right? The energy moved. Something moved. And it was this energy. It wasn't the molecules itself. Note that the molecules here are still here. They never moved. I'll come back to my longitudinal wave machine here, right? These rods here never move over to here. There's a vibration that then gets sent over to here. There is a flow of energy. There's a movement of energy. That was our definition of a wave in chapter 15. So clearly these sounds are waves, so we call them sound waves. And clearly they vibrate in the direction they move, so clearly they are longitudinal sound waves. So that's the first part of this. In fact, you can kind of now begin to see how you would make a wave and sound wave, and how you would make and detect a sound wave. So any kind of detector has something over here that then when it gets hit has the ability to move. And the whole reason we call it an eardrum is because it really looks like a drum. It looks like you put a tarp over a round object, pulled it taut, and then when the waves hit it, they make that material shake in exactly the same pattern that it's being hit, and it's being hit by exactly the same pattern that is generating them back here. So to generate waves, we have to have something that is moving, something that is vibrating, something that is pushing on these molecules. And then, of course, detect them, we have to have something that would move. So our eardrum does that, but also so does our microphone. So this lapel mic has probably inside of it a little tiny piece of what, if you want to call it a drum, you could. It's just probably a round disc that has a piece of plastic on it. And so as the sound waves from my voice push it back and forth, it moves that piece of plastic. Now, in addition to that, that piece of plastic probably has a coil and a magnet, and so one of the things we'll learn as we get to electricity is that if you move a coil and a magnet, it makes electricity. So the mechanical movement of that piece of plastic is then converted into electricity because of that. There's other ways to make a microphone, so I'm kind of guessing what might be in here, but I guess I'm not 100% sure. But that's kind of the simplest way to make an electric microphone. But like I said, hopefully this is just giving you a picture of how the waves are. And we want to study not so much how you make them and not so much how you detect them, but what are they? And so it's the part in between the creation of the waves and the detection of the waves that I want to talk about. What are sound waves? Of course, in all of this, you begin to see that not only are you transmitting energy, but you're also transmitting information. Because whatever pattern these shake at, that's what the detector will shake at. You already heard that, but I'll show it to you again. These two pieces of metal, they're both made out of aluminum, but they do shake at a different rate. These have been measured and we've stamped on here, but when I hit this, this goes back and forth 512 times in 1 second. Whereas this one goes back and forth 1,012. Can you pick that up at all, right? Oh, good. So there's 1,012, I'm sorry, 1,024. This is 512. Now, hopefully, let's just go back to our mechanics for a moment. It doesn't surprise you too much that this one would be 1,024 times, because notice that the aluminum is thicker and therefore stiffer. It's also shorter, and so remember that whole moment of inertia thing. And so I would expect that these metal pieces would be harder to rock back and forth than these because they're a little longer. And these would also go back and forth a little bit faster because they're stiffer, they're thicker metal. They're actually the same type of material, aluminum. So I'm not comparing a stiff metal like steel to a softer metal. The aluminum's not real soft, but it's relatively soft. But there's a lot softer ones. And so this right there, just looking at the mechanics of it, would tell me this should go back at a higher rate. And sure enough, as I said, it does. This is... This was 1,000. And can you still hear me? Yeah. So this is the 1,000 and... straighten it up. 1,024. This is the 512. And couldn't you tell the difference between those two? At least I hope that comes across on the video. Because as it gets recorded, and then of course you're playing it back, but as it is playing back, it's actually making the speakers on your stereo go back and forth at that rate, and it's pushing them at a different rate. And so that is what pushes on your eardrum. And without getting into a biology class of how then the eardrum work, it'll eventually then get registered in your brain, and your brain is beginning to tell you, oh, there's a different rate. There's a different frequency. And so in this last chapter, we had talked about frequency. Frequency was this rate going back and forth. So I had one tuning fork that went back and forth 1,024 times a second. And what I'm saying is that tuning fork, this one here, is then creating sound waves with a frequency of 1,024 hertz. Now the other one is half of that at 512 hertz. And so these are the two. I actually have a lot more, so depending on where I go with this, I can get a lot of different frequencies of this. But the thing I want to get across to you is that it doesn't really matter what rate this is. This rate could have been even higher, like 2,000, or could have been lower, like say 100. I would still call them sound waves. And so I could even make kind of this chart, kind of a number line, a one-dimensional chart, if you will, and say, all right, let's list the different rates they can go back. But now that I've done, I think, the first step of sound waves, what are they? There are these shaking or these vibrations of these atoms. I'm hoping you see that I'm going to call it sound waves, whether or not it's at a high frequency or a low frequency. And so the two that I've done maybe fit right here. Here's the 512. Maybe this is the 1,024. But I'm going to put kind of a little magical line right here. And maybe another magical line right here. Because if I'm getting my point across, I would say any shaking that then makes these air molecules vibrate back and forth are sound waves. There are categories that, for instance, your brain can only detect. And so my eardrum is designed that it can pick up shaking really as low as 20 and as high as 20,000. However, the physics of sound is much bigger than that. Could there be sounds way out here at 30,000? Sure. Now that would be a heck of a lot of vibrations in 1 second. I get that. But I would still call it sound waves. Could I have sound waves way down here that maybe only go back and forth 5 times in a second? And I want to say, sure, I could. And in fact, this is kind of fun to actually play. I don't know how this is going to come across on a video, but in the classroom, it's always kind of nice to hear this. This region right here is kind of special because it's what the human ear is designed to hear. And so in a moment, I'll create a bunch of these different frequencies, everywhere from, as low as 20 to as high as 20,000. But I want to emphasize and say it again, could there be frequencies greater than that? Sure. So let's give it a name, since we're going to use the word sonic range for what the human ear can hear. And so anything that is greater in frequency than 20,000, anything that's greater in frequency than the human ear can hear, well, let's refer to that as ultrasonic. Now, by the way, notice I didn't say supersonic. Supersonic is a word we're going to say for speed. I'm not talking about the speed of sound. I will soon. But so far, I am not talking about the speed of sound. This is the frequency of the sound. Maybe you're familiar with the word ultraviolet. When we get to light, you will see that we call it violet because that is our human brain telling us that the frequency is, and it's a high frequency. And there are frequencies higher than the violet, so we call it ultraviolet. Our human eye doesn't detect it, so we just, give it a name and we build detectors with it. And there's other animals like insects that are really good at detecting ultraviolet light, but our human eyes don't. And so that's a word that ultrasonic and supersonic, hopefully you don't confuse. Supersonic, we're going to say something that is faster than the speed of sound. Okay, so let's talk about speed later on. And then likewise, over here on this end of the spectrum, we could have frequencies lower than what the human ear normally hears. And so a good name for that is the infrasonic. And again, do not call it subsonic. Again, subsonic and supersonic are related to speed. And I'm not talking about speed. I'm talking about the frequency. I will talk about the speed soon. But right now, I'm talking about the frequencies of them. So we usually take our sound waves and put them into these three categories. The sonic range is what the humans can hear. But then we have things lower than the human hears, so it's infrasonic, and things greater, it's ultrasonic. Maybe you're even familiar with the word infrared. Because again, as we get to light, you will see that we will call it red because it's a low frequency. That's the lowest the human eye can see. So lower than that, we'll call it infrared. So we do the same thing with the visible light as we do for the sound waves, and that is the infra and ultra with the word sonic in here. But let me just kind of play a bunch of these. Obviously, the ones that are infra and ultrasonic, you're not going to be able to hear, even if you were in the room, and my microphone's not even built to pick up those, since the microphone is just built to pick up in the sonic range. Let me come over here and show you probably what you might call the most common way of making sound waves today. I don't know if you will recognize this, but this is a speaker. And so if you have any kind of instrument that plays sound, usually there's a cover over it so you don't see it. But if you take it apart, and this is out of a big stereo speaker, you've got this thing. It's a speaker. And on this one, the paper diaphragm was glued to the edge, and we deliberately ripped it off so that you can get a better understanding of sound waves and how speakers work here. Here really is what's producing the sound. It is this paper diaphragm that if it moves back and forth is going to be the equivalent of a tuning fork. Here the tuning fork, the metal pieces move back and forth. But here we use this pretty light paper diaphragm to move back and forth. And of course, the way we do it, and a little bit earlier, but as we get into the electronics, we have got a coil of wires back here. So we've got a bunch of wires wrapped around. And one thing we'll learn as we get into electricity and our magnetism, where do I do with my hammer? Is that also in this speaker is a magnet. And so there is a very large magnet at the base of this speaker that, if you've ever played with magnets, you'll know that when you put them together, they either attract or repel, depending on how you align them. And that's what goes on here with this paper diaphragm. We've got a permanent magnet in the metal housing here, and on the paper diaphragm, we have a coil. When you put electricity through it, this makes it a magnet. And so this will make the paper diaphragm either attracted to the magnet, so pull this way, or repelled from the magnet, pushed out that way. And so this paper diaphragm then can move back and forth depending on how we change the electricity in this coil. And so that's why all of our speakers need then some electrical connections, and on this old one it would be right here. So that broken speaker works really well to kind of demonstrate that, hey, I'm going to make sound waves by making something vibrate. It's a paper diaphragm, and I'm going to use the electricity going through a coil and a magnet to push the paper diaphragm. So that's why I've got this speaker, which isn't quite broken. It's a little broken. I did punch a little hole in the paper here so that I can still demonstrate to you that there is a magnet on here, and it holds this metal piece. But the paper diaphragm, I didn't take off the glue, and so it's still here. And if I kind of hold it in the camera, you might even be able to see if I pull on it, it can move back and forth. You might even be able to see where the wires come in here. Then they go back and you can't see, but under here would be the magnet, and this coil then would be next to that magnet. So if I take a little electronic box here, and so here's my electronic box, and my electronic box then can put out electricity forward and back at some rate. Maybe I will set this at a rate of, how about roughly 5, since I put 5 there on the board. Oh, it looks like 7. Maybe 7's a good one. But if I hold it up to the video camera here, make sure it's turned all the way up. And, this one has gotten a real bad tear in it, and a tear here. It's time for me to get a newer one here so we can hear our sounds a little bit better. But this paper diaphragm, I'm hoping you can kind of see it looks like it's breathing. It is going back and forth. And the number here on the screen is a 7. And what that is saying here is take this electricity and at a rate of 7, so 7 hertz, put the electricity forward, back, forward, back, forward, back. And so that would make this an electromagnet pushing the paper diaphragm forward, back, forward, back. And so I would say right now I am having a speaker, and I would even say I am producing sound. It's in the category, though, of infrasonic. And so from a human perspective, I'd say, well, that's not producing sound. It's just kind of moving. In fact, you might be able to pick it up on my lapel mic, but as it moves, it kind of shakes the little pieces of paper, and I can kind of hear that shake, but I don't actually hear the 7. This little setting right here can go up to, I think, about 22. But when I get to this area of 15, 16, or 17, I think you can see it a lot better. And you can see this. I don't know if it's better to have it at an angle so you can see it, or straight at the camera. You can kind of see it breathing going back and forth. And so again, I'd say I can't hear anything with this. Now I could build special equipment that can pick up infrasonic. There's other animals that have different types of eardrums. A good example are elephants. Elephants are really good at hearing in this range, but not us. Excuse me, not us humans. And so this particular setting goes as high as 22. And 22 is kind of at the cusp of being able to hear it. If you were in a room setting here, you probably wouldn't hear it. Your ears are just getting ready to hear it. You guys are probably still all young, so it's probably not a hearing problem. But obviously, the older you get, you may not be able to hear it. Although usually old hearing problems occur at the high frequencies, not the lower ones here. But this is the 22. See, now I think it gets more interesting. Let me turn the dial down and I'll go to another setting. This multiplies it by 10. So if that last one went up to 22, this one will go up to 222. And so now you'll begin to hear it. And let's see, normally I point it out towards the room, but maybe I'll point it towards me now with the lapel mic. And you probably, oh good, Ron's giving me the thumbs up that there's some sound coming through. And we're at 37 here on the dial. And if I turn it up a little more, you hopefully will hear a change. We're at 41. I'll do a little more. 43, 48, 55, 62, 72, 83, 92, 103, 113. And let me just go through the rest of this dial here. 122, 123, 134, 150, 159, 170, 186, and I'll just go full dial, which I think will be 220. Looks like 217. And so now you're hearing 217. Let me stop it for just a moment. Because didn't it sound different? I'm trying to point out that these are all really the same physics. They're all the same sound waves. But your brain, your ear and your brain are able to distinguish that rate. And in fact, if this wasn't a science class, you probably wouldn't have used the word frequency to describe that. You would have probably called it pitch or tone. And so I want to point out here, whoops, that's a terrible picture there, that the frequency is the tone or the pitch. And so when you hear different sounds, the physics, different tones, the physics is still the same. Of course, then your brain has this mechanism to tell you, okay, this is a low frequency or this is a high frequency. And if you want to substitute the word pitch in there for frequency, feel free. That's exactly my point here, is that now that we know all this stuff about waves and everything we said about frequency, if we talk about sound waves, you could just change the word frequency to pitch or to tone. And so tone is synonymous with frequency. Well, let's come back to here because, again, I think it's kind of enlightening or worth hearing this for the first time. And so I'll turn it back on here. As I said, this is the 217. Let me just turn it down again and go to another setting. So I'll turn it down. And hopefully you can even hear that there as it changed the frequency. Let me hit another multiple of 10. So this one should go to about 2,200. So let's just run through this dial. So we'll start at low at about 20. And this will change quickly. Let me get back to about where we had left off. So that's about 214 right there. 275. 325. 400, 417, 480, 612, looks like 732, and it's probably sounding like a high frequency to you, but we're not really high. Remember, human ear can go to 20,000. We got a long way to go. Maybe I'll just shut it off here for a second, but that gives you an indication of what the human ear can detect, right? The human ear can detect a huge range, and most of the stuff we hear is probably under that 700, so somewhere in that range of maybe 100 to 700. But let's just go to our 2,000. All right, so 750, 920, 1,000. 1,200, 1,300, 1,470, 1,575, 1,800, 19. I'll just go full dial and see how high it goes. And so that's pretty close to 2,200. In fact, I don't know if it's quite obnoxious on your end, but it really is on this end. And so let me shut that off there because it's really a high frequency. But again, let me say it again. What I hope I'm getting across here, and we got a long way to go to get to 20,000 still, is that we are seeing here the sonic range and these higher and higher and higher and higher frequencies. And so frequency goes with pitch. That's what I want to emphasize. Maybe I'll come back here so I don't have to keep coming back and forth. But let's try this again. And so I'll turn it on. And I'll turn down the dial again. Okay, to 0 frequency, or as close. And let me go factor of 10 again. This one, its lowest is about 240. Okay, so I'm going to start at 240 and keep going. And there's about 500, 700, 800, 1,000, 1,500, 1,600, 17, 18, 19, 2,000. Now we're getting into some new stuff. This is 2,500, 3,000, 4,000. I suppose the only blessing about this, because it really gets more obnoxious the higher the frequency is, and so we're at a really obnoxious high frequency. Again, depending on your speaker system, I don't know how it plays back, and also depending on the quality of this mic, but that is really annoying. But on the good side, your ears are beginning to hear less of it. So they're not as sensitive here at this point. And so it's a combination here. And so I don't know if this is better or worse than the 2000. The 2000 is really annoying because I can hear it really well and it's a high frequency. This is 4000. This is as annoying. It's higher but less in volume. At least that's the way my ears interpret it. And we still got a long way to go. We're only at 4000. All right, so 4000, 5000, 6000, 7000, 8000, 9000, 10. And I really don't know how well this microphone will pick them up. Can you hear things, Ron? Very faint? Okay. And that's too bad because I really like this 13,000 right about here. Usually this is a point when I point it at students, they just kind of cringe. Oh, like, oh. And it's kind of neat to hear just one time in your life and get an idea of 13,000. In fact, it's really getting obnoxious. I'm going to shut it off here for just a second so I can talk over you. But I like this one because this is about where people at my age start to lose their hearing and they start to lose this ability to hear this high frequency. So my son thought that would be cool, and he, when he was in high school, set this as his ringtone with the idea that he could be the